We are Team ZipFizz, also known as Group 5 from Section 17. Our team consists of Christian, myself Karadu, Robert, and Thomas. The goal of this project was to create standalone measurement systems in order to test the accuracy of our given sensors and to attempt to calibrate these sensors through our created systems. The design requirements we followed were rather straightforward. Each system needed a control measurement tool, such as a ruler or thermometer, and a corresponding code written to operate the created system and display values on our LCD and on our gauge display created from our servo. Our team approached this project by first designing systems that can incorporate the given sensors and some sort of control device so we can measure the values from 2 different points. After we designed our systems, we wrote code to run each system and display the values that were obtained from our sensors on our LCD and gauge display. While we obtained the values from our sensors, we simultaneously measured their outputs manually through control devices. We then compared our values to test the accuracy of our sensors.
To set up this experiment, we took 3 containers and filled them each with water at different temperatures, one at room temperature, one with ice water, and the other with near boiling water. And we placed the temperature sensor in each container, along with a thermometer to use as our control. And the water temperatures were then taken and used to calibrate our measurement device. This is our circuit diagram with our LCD screen and our thermistor and a 10 kilo ohm resistor connected to the Arduino Uno R3. And here it is displaying the temperature of the ice water using our thermistor, and there it shows the temperature in Fahrenheit on the thermometer. Next up we have the room temperature water, and you can see it displayed here next to the thermometer in Fahrenheit again. And lastly we have the near boiling water. Right now it's at room temperature, and you can see when the thermistor is dipped into the water, it moves up to around 70 degrees Celsius. And there it is displayed on the thermometer in Fahrenheit again. This is our code for the temperature display readout. It starts by declaring the liquid crystal pins, and then in our setup we initialize the LCD and light up the background. Then the input is taken into a loop function and it's converted into Kelvin, which we then use to convert into either Celsius or Fahrenheit, which can be changed towards the bottom of the code, whether we want to display, again, either the temperature in Celsius or the temperature in Fahrenheit. And finally, at the end of the loop, there's a delay for 500 milliseconds so that it runs every half second.
Here we have our design steps for our contactless distance measuring system, which is the ultrasonic sensor and a servo motor as a dial. And here we have our circuit diagram for the contactless distance measuring system, which is the ultrasonic sensor connected to the breadboard and the Arduino, and the servo motor connected also to the breadboard and the Arduino, which acts as the dial. And now you can see our actual setup of our experiment. We have a meter stick with the ultrasonic sensor directly on top of that. The meter stick is used to measure the actual distances, and we also have our dial, which uses a servo motor to tell us the distances. And we have our object, which is used to change the distances from the supersonic sensor. One of our biggest problems was getting a consistent reading from faraway distances and very close distances. To mediate this, we used a larger object and a more flat object in order to get more consistent readings. To calibrate this system, we took the actual distances and compared them to the distances that was output by the supersonic sensor, therefore determining what to change in the code to get a more correct reading. Now this is the code for our ultrasonic sensor. At the top we define our constants like our pin numbers and our maximum distance that it's going to read. And then we call the ultrasonic sensor with it then outputting its distance in centimeters, then calling the calculate distance function to change that number into degrees from 0 to 180, to then tell the servo which position to be in corresponding with the set distance.
For our third system, we had a water level depth sensor. Our system consisted of a container filled with water in which a ruler was placed, and water reached the top of the parallel conductors on the sensor. The sensor was connected into the Arduino through the S signal VCC power pin and the ground. And on the Arduino side, we had the ground, 5 volt, and analog input 3. For the calibration of our water level sensor, we dipped the sensor into the water at the maximum, and then we viewed the max value given from the sensor. In our case, that was 390. This value correlated to the voltage through the sensor. With the use of a constant 4.1 that we found experimentally, we calculated the depth in millimeters through the sensor's voltage level. That the sensor works by bridging the sense traces and power traces on the sensor when submerged in water, and we also faced a problem when the sensor was not completely dried off before being redipped into water. Knowledge learned from our system could be used in sensors in manufacturing, specifically position sensors, which change linearly. In our code for the water level sensor, we have our initialized variables, some of them being the ADC ID equals 0, our initial position for the servo equals 0, and then our value equals 0 from the sensor. Then below we have a loop in which we get the value given from the sensor, and we multiply by our constant and divide by our maximum 390 to then give us a height of the water in millimeters.
There were many principles learned throughout this experiment. The first thing our team learned is the importance of having proper calibration on our sensors. For example, our ultrasonic sensor was extremely sensitive and took a decent amount of setting up in order to get it to properly display a distance that corresponded to our control device. Even with proper calibration, our team learned that these sensors are not 100%. Even by doing everything possible to make them accurate, there were still some discrepancies in our sensor and control data. We contributed these discrepancies to the fact that some sensors can have some design flaws which make them less than ideal during operation. This experiment had lots of significance in presenting the team with the importance of testing sensors. There are various applications where a sensor must be perfectly calibrated in order to work. For example, most cars run off of a mass airflow sensor, which measures the air going into the throttle body and transmits that data on a 1 to 5 volt range, which tells the car how much fuel to input. If the mass airflow sensor is not perfectly calibrated, the car will have issues running at lower RPM and can result in mechanical damages.